high-speed rail is at the forefront of transport technology. Today's machines are the result of over 200 years of innovation and craft. Countries around the world are now locked in a battle of technology to produce the fastest and best railway system on Earth. In America, more than anywhere else, the unstoppable rise of the automobile and the plane over the last century has beaten the train into near submission. But with gridlocked roads and crowded skies now a daily occurrence, train technology is again making a comeback. In the year 2000, Amtrak unveiled their answer to the 21st century's transport problems. The Acela Express represents a new dawn for American travel. The Acela is faster than any train America has seen before, travelling at 240 kilometres an hour along a 100-year-old route known as the Northeast Corridor. Inside, the passenger car is smooth and near silent. Only the view tells you the speed. But as any train driver will tell you, nothing beats the sensation you get sitting up front.
It's a rush. I mean, you get on the train and it accelerates, you get up to 150 miles an hour, and it's kind of like flying on the ground.
To achieve 240 kilometres an hour, the Acela draws over 9,000 kilowatts of power supplied from overhead lines. The locomotive houses an enormous traction motor and is shaped for aerodynamic efficiency and stability.
The Acela is very, very technically advanced because of the onboard computer systems that we use to actually operate the train, the computers that the engineer uses to control the speed of the train, the acceleration.
When you're driving an Acela, you're at the helm of over 500 tons of steel and over 300 lives. At the Amtrak headquarters in Wilmington, Jay Gilfillan instructs engineers how to drive at 240 kilometres an hour. This simulator replicates every detail and sensation of driving the real Acela.
I think the hardest part is that there's so much that you have to do at one time, so many things you have to look at, but it's once you get the feel of it, it's just like driving a car. It becomes second nature to you. The acceleration rate is phenomenal because we actually have two power cars. There's the one that we're in, and then there's one on the other end that's pushing. At some of the speeds that we're going, 150 miles an hour, it will take me almost a mile to get it stopped. We're going the length of a football field in 3/4 of a second, so there's no time for games up here. It's very serious business.
The Acela's top speed is limited by the old twisty tracks of the Northeast Corridor. To maintain high speeds on the bends, the Acela carriages are designed to lean into the corners like a row of cyclists. As a result, it can corner 30% faster than other trains along the route.
As the car goes into a curve, the car will literally tilt or lean to compensate for the gravitational force of going around the curve. And then when it gets back out on the straight, the computer will say, okay, straighten the car back up. On the power car is a transducer that measures acceleration, deacceleration, the lateral G-forces, and it'll take that information and send it back to the computer on board the coach for the tilting system and tells the computer, okay, I need you to tilt X number of degrees based on how fast we're going and the lateral forces that we're experiencing.
Amtrak is confident that their new high-speed train set will make a significant dent in the fortunes of the airlines. From downtown New York to downtown Washington, D.C., the Acela claims to be able to get you to your destination faster than any of its rivals. So we decided to put their claim and their train to the test. Every day, tens of thousands of people make the journey from New York to Washington, D.C. And the best way to get there is a matter of hot debate. Meet Hadley and Sarah. Hadley Wasson prefers to make the journey by plane. Sarah Sattel swears by the Acela Express. They're making the same journey from the Empire State Building to the White House, and it's a race to see who gets there first.
Let's go. 1, 2, 3.
Hi, JFK Airport, please.
Penn Station, please.
Sarah's short journey to Pennsylvania Station in the heart of Manhattan should take minutes. Hadley, on the other hand, has to take a cab to JFK Airport, 27 kilometres from the Empire State, through New York's worst traffic bottlenecks. Once through security and check-in, Hadley's flight will take her direct to Reagan Airport. Sarah will board the Acela, riding the 370 kilometres to downtown DC by train. Then it's a race by taxi to the White House.
I prefer flying because taking the train can be more expensive than taking a plane.
The time that you save really isn't all that much, and I don't think you even do save any time.
The only irritating thing about flying is having to go through security.
Hadley's going to be left in the dust. Sarah's going to emerge the winner.
Oh, I'm going to win.
They're both sure of success, but who will get there first? We're minutes into a race between the airlines and America's new high-speed train. With the station situated in the heart of Manhattan, early indications are good for the train. Hadley is stuck in traffic on her way to the airport, and Sarah is already getting settled on the Acela Express.
We are less than an hour into the trek down to DC. I'm pretty sure I'll beat Hadley there because the train's on time. She does only have an hour flight down to DC. She'll have to face traffic though. Got my seat, relaxed. I can pull out my laptop if I want, chill out, listen to my iPod.
Two hours later, and the tables have turned. Despite having to travel further to the airport and having to wait longer for her flight, Hadley gains on Sarah once she's in the air, travelling at 850 kilometres an hour instead of 240 on the ground. As they approach Washington, D.C., Sarah and Hadley are just minutes apart. But with Sarah's train only just arriving at Union Station, Hadley's taxi has already dropped her at the White House. So on this journey, the plane beats the train by just 10 minutes, almost too close to cool. But now a new high-speed train might just tip the balance. As an electrically powered train, the Acela is currently confined to the northeast corridor. But now a new model in Canada has borrowed a trick from the airlines. It uses jet age technology to generate enough power to conquer the non-electrified routes in America as well. The jet train.
We are able to reach high speed, we are able to reach acceleration comparable to electric train in operation today, but we don't need the electrification that's normally required for those trains.
On the outside, the jet train looks exactly like the Acela. It's not until you board the locomotive that you can spot the difference. Engineer Daniel Hubert explains.
Essentially, this is exactly the same cab as the SLA power car that's presently in operation on the Northeast Corridor. The only difference would be this small button here.
The black switch controls this train's secret. Housed inside a soundproofed compartment, a jet turbine engine.
This is the art of the jet train locomotive. It's a PW 150 derivative that can develop 5,000 HP, which is the equivalent of about a 50 car engine.
The turbine itself was extracted from a working aircraft and now powers the train by producing electricity to drive the motors. It's so efficient and lightweight that the jet train can match the top speed of the original Acela.
It's that combination of high power and low weight that enables us to go at the fastest speeds possible. We've tested it at Pueblo up to 250 kilometers per hour, or 156 miles per hour. We also have the tilting technology that enables to go faster in curves and also provide much better passenger comfort.
If it fulfills its potential, the jet train could be running throughout America within 5 years. Britain is the birthplace of the train and was instrumental in developing many of the world's first high-speed trains, despite having the oldest and possibly twistiest network in the world.
The Silver Jubilee, drawn by the streamlined Silver Link, left King's Cross. She is to run regularly between London and Newcastle, and on her trial trip she attained a record speed of 112 miles an hour. Speed, comfort, and a wild modern beauty.
Thanks to its rich rail history, there are some 100,000 train spotters in the UK. They are all fiercely proud of their railway heritage. And this man is no exception.
I was never actually a train spotter, although I do like big lumps of technology, and a train is actually a big lump of technology.
Bruce Dickinson is a train enthusiast with a passion for high-speed rail travel. He rides the world's high-speed trains whenever his job permits. Bruce is rock band Iron Maiden's lead singer.
We're going to do a song now. We want to dedicate it to everybody.
Despite fame, fortune and cult status, he still finds time to indulge his very British passion. His all-time favourite is the Intercity 125, a model of reliability and speed.
Well, I have to say, I have a big old soft spot for the relatively, obsolete now, bless it, but the old high-speed train, because it was one of the very first high-speed trains, and it was also, it was an independent power source. It wasn't dependent on, electrical power and pantographs and things like that, and it rocked along at a fair old lick.
But Britain's high-speed trains have always been limited by the age of the network, unable to reach the highest speeds on their twisty Victorian tracks. To overcome the problem, British Rail launched the Advanced Passenger Train, the APT. The world's first tilting train, it was a huge success when it was introduced in 1979, breaking the UK speed record at 261 kilometres an hour. But the APT was withdrawn from service a few months later, thanks to bad publicity after the tilt mechanism stuck with journalists on board. Over 2 decades later, and tilting technology is back on track in Britain. The Pendolino, developed by Fiat, tilts up to 8 degrees and maintains an average speed of 240 kilometres an hour. Like the Acela, its advanced computerised systems switch off the tilt at critical moments en route to prevent the train from colliding with tunnels, bridges and other trains.
The Brits have always had a love-hate relationship with technology. We love inventing it, but we hate exploiting it. And, you know, you can almost look at the movie The Italian Job and say, well, unfortunately, they've tucked us up good and proper now, because they're actually selling back our technology back to us in the form of the Pendolino, which Virgin has brought, you know, because of our higgledy-piggledy twisty tracks. We're stuck with Italian technology, not a bad thing necessarily, but just a great shame, because the APT was potentially a fantastic bit of kit.
As new high-speed trains like the Acela and the Pendolino get faster, so designers plan to develop better braking systems and more effective impact strategies. Today's systems use complex computer networks to keep the trains on course and several kilometres apart. But sometimes the only way to advance the technology is to test it to destruction. Crashing trains is a crucial part of assessing how the structure of the carriages react under the forces of impact. Thanks to tests like these, train designers now know, for example, that there is a far greater chance of neck and spine injuries in forward-facing seats.
When Amtrak designed the Acela, they weren't only concerned with how fast can we go. Their primary concern was the safety of the passengers and the safety of the engineers. The cab of the locomotive is designed in such a way that there's actually a built-in refuge area that, in the event of a collision, that the engineer could go to for his safety, and the locomotive would basically crumble around him. There's crumple zones designed into the cars. There are energy-absorbing devices. Part of the knuckle is a hydraulic energy-absorbing device. There are buffer plates between each car to absorb the impact. I don't want to say it, but it's designed to withstand an accident. The American trains are built primarily out of steel, where the European trains, I believe, are a lot of aluminium-type metals, which are a lot lighter, and they're able to go faster, but they won't withstand an accident as well as... It's kind of like if you're driving around in a tank in a Volkswagen and you run into a telephone pole. I'd prefer to be in the tank.
When trains crash for real, it's easy to understand why designers put so much effort into protecting passengers. But it's not always the train that's to blame. If the track breaks or cracks, there is little that can be done to stop a train derailing. In October 2000 at Hatfield near London, a technical failure caused a high-speed accident on an Intercity 225. It would have lasting repercussions for Britain's railways. Bev Adshead had recently started a new job as a buffet attendant on the train.
You read about these things, they don't happen to you, they happen to somebody else. And suddenly, this thing's happened to me.
At 12:10 p.m. on October the 17th. As the train rounded a bend at 185 kilometres an hour, a rail under the carriages cracked. The train derailed, overturning as it ploughed into the ballast.
I just sort of grabbed hold of this doorway, hoping that I wouldn't slide back into the window, and just really hoping that train would either stop or that I'd just go unconscious so I didn't know anything else.
The buffet car was thrown into the air before coming to rest in the undergrowth 15 seconds later.
We actually climbed out of the roof, so half of that carriage, the roof was literally ripped off.
It would highlight a major problem for high-speed trains everywhere, that heavier, powerful locomotives cause more wear and tear on the track. As a result of the Hatfield tragedy, the entire rail network in Britain is being overhauled and improved. And the rail companies are determined to develop new technologies that will make their tracks safer. In Britain, independent inventor Malcolm Higgins is developing a machine that will help combat rail fatigue by cleaning rails without damaging them.
I didn't know anything about lasers, I didn't know anything about trains, I'm not an engineer, so I seemed well qualified to take this idea forward.
High-tech, mobile maintenance is the key to keeping high-speed trains on track. Currently, the biggest problem rail operators face is keeping rails free from damaging leaf residue.
You can see here a fairly typical example of dirty rail. The black area here gives some idea of what leaf residue looks like. Vortices along the side of the train pick up the leaves and actually force them in between the wheel and the rail. Repeated roll-ins of the wheels actually roll them into this Teflon-like coating on the surface. Then when you get water on it as well, it becomes like a skid pan.
Delays caused by leaves on the line have become a national joke in Britain, but in reality they occur in every country and can make trains skid through red signals. Currently, rail companies use high-pressure jets of water and sandite, a kind of abrasive gel, to try and combat the problem. But this method is not 100% efficient and comes with its own set of problems. Leaving behind tough grains of sand only increases the chance of track fatigue and the potential for damaged rails. Malcolm's invention will revolutionise the whole approach to rail maintenance. For 4 years, his team have been experimenting with laser light as a means of stripping leaf residue from the rail. Soon, it will be tested out on the real rail network.
First of all, we have the laser itself. This laser is just a prototype version at the moment. Effectively, we will be producing power that's 10 times more than this type of lasers produced before in the world, which is an awful lot of energy to have to control. All of this is delivered through a fibre optic cable, which routes its way down through the container to the railhead, and that's where the business end is. Here we have the fibre optic coming down into something called an optical box. We have here 25,000 pulses of light a second being delivered onto the track. We're keeping the light contained by this bottom shoe that protects us all and makes sure that the light that we're using doesn't cause any damage to our eyes or indeed to any little furry animals that might be by the side of the track or anything like that. Each little pulse of energy that we deliver is 5,000 degrees centigrade, but all of that energy is absorbed by the contamination that's on the railhead. So if you put your hand on straight afterwards, you wouldn't feel any heat in the process at all.
Malcolm's invention could be fully operational within 2 years. But there is one foolproof way to avoid problems with high-speed corners and faulty rails altogether. Completely rebuild the network. The world's fastest trains are designed to run on purpose-built, straight track and have broken records in the process. The fastest railways in the world have tracks built specifically for them. Exclusive, dedicated tracks, free from sharp bends, incur less wear and tear and make the system much safer too.
The Japanese really came up with the concept of a dedicated track and a dedicated trains that went very fast. It really was a revolutionary concept. It was market driven by the numbers of people that simply want to move from A to B to C to D, all in a straight line. That makes it a doddle to design a train to do that.
For over 30 years, the Shinkansen bullet has been rocketing between Tokyo and Osaka at 257 kilometers an hour, until recently quicker than any other train system on Earth. For train designers planet-wide, the bullet has proved itself as the icon of high-speed train travel. Like the bullet, the French TGV system relies on fast trains running on specially built straight tracks. These trains don't need to tilt as the system has done away with sharp corners completely. The TGV, or train à grande vitesse, is the modern champion of speed, regularly topping 274 kilometres an hour. During tests in 1990, an experimental TGV hit a staggering 515 kilometres an hour, setting a new world record.
Félicitations! Sortez le champagne!
The TGV's secret of success is in its engineering. There are half the number of wheel assemblies, known as bogies, giving the carriages an ultra-low centre of gravity and vastly reducing the overall weight and friction of the train. The TGV is also possibly the safest train system in the world. The positioning of the bogies reduces sideways forces on the carriages, making derailing much less likely. Part of the reason that it has never been involved in a fatal accident. It's truly a source of envy for France's neighbours.
We somehow got caught up in all the red tape and were unable to do something as simple as the French, which is put one pantograph on the front of the engine and run a cable down the train and power the back car. And that simple piece of technology enabled the TGV to get up and going, and they could just clamp multiple units together and run huge trains throughout the length of the network.
In the not too distant future, French technology is set to revolutionise rail travel for one of its neighbours. Currently, a fleet of 27 multi-million-dollar Eurostar trains connect France and the UK through the Channel Tunnel rail link. An adaptation of the TGV, the Eurostar locomotives generate power equivalent to 130 car engines as the train hurtles towards the French side of the tunnel at 300 kilometres an hour. Now, new Eurostar track is being laid between the Channel Tunnel and London to bring trains on the English side up to speed. A massive civil engineering enterprise that has involved uprooting whole villages. When the new link opens, trains will travel at 300 kilometres an hour for the first time in Britain, and a journey from the heart of Paris to the centre of London will take just over 2.5 hours, shaving 20 minutes off the current time. High-speed train systems that run on dedicated track are so reliable that accidents are extremely uncommon. But at these kinds of speeds, one tiny flaw can lead to catastrophe. The Intercity Express is Germany's answer to the TGV. It uses lightweight alloys, tilts like the Pendolino, and has a top speed of 280 kilometres an hour. When the ICE derailed in 1999, it became the worst German rail disaster in 20 years. Travelling at 200 kilometres an hour, the fourth carriage derailed, sending the rest of the train ploughing into a bridge. 102 people died. What nobody had accounted for was an unexpected fault in a new type of wheel called the Bochum 84. It was a tragic end to the ICE's 100% record for safety. The ICE accident highlighted a problem that all railways face, that mechanical parts can fail without warning. If you want to go even faster and remain safe, modern thinking suggests you have to do away with rails and wheels altogether. In Japan, this experimental train with wings works on the same principle as a piece of paper dropping to the floor. It's kept afloat by a cushion of air. The aero train has no brakes. It has to use a parachute to stop. Even more ingenious, researchers are developing trains known as maglevs that also skim above their tracks, this time suspended on a cushion of magnetism. In 1999, an experimental maglev in Japan sped to 552 kilometers an hour, breaking the passenger train world record previously held by the TGV. Magnetic levitation was first developed in the 1960s by British inventor Professor Eric Laithwaite.
This is a linear motor, and that's just a fancy name for a row of electromagnets. This is a sheet of aluminium. When I put it on the motor and switch on the magnets, something pretty dramatic occurs. If I try and put it back now, you see I can hold it with finger and thumb because it tries to float. But it isn't stable sideways. If I get it a bit off center, it tends to fly off. Let it go, and there you have propulsion without physical contact.
Like Laithwaite's linear motor, the maglev track contains a row of powerful electromagnets that create enough upward force on magnets in the train to lift it into the air. And that when switched on in rapid succession, provide enough horizontal force to propel it forward. To brake, the magnetic field is simply reversed, and magnetic forces act on the train in the opposite direction. Today, a prototype in Emsland, Germany, carries passengers around a 30-kilometre test track at super high speeds. Maglevs don't need to tilt. The track is already steeply banked to 12 degrees to accommodate high-speed bends. There is no motor on the train, it's in the track, making the maglev far lighter than normal trains, and even though it consumes a third less power, its acceleration is 4 times better than the TGVs. And with no wheels touching the track, friction is minimal. There is no danger of rail fatigue or wheel failure, and the train can reach astonishing speeds.
People often ask what is the maximum speed possible for a maglev train. Today it would be possible to maintain higher speeds of about 600-700 kilometers per hour. Germany is famous in the world for engineering capacities, but I think even in other countries it would have been possible to build up or develop a system like this.
Maglev technology already has truly international appeal. The German design is on a fast track to China. The world's first commercial maglev between Shanghai and its airport opens in 2004, reducing the journey time from 45 to 8 minutes. The system is expected to carry 10 million passengers, rising to a predicted 20 million by 2010. If it proves a success, China plans to build a massive intercity network of 435-kilometre-an-hour maglev trains to ease the burden on its overcrowded transport system. For the future of maglev technology, the sky is quite literally the limit. In America, scientists at NASA's Marshall Space Flight Center are developing a maglev train that could propel their spacecraft skywards. Heading the team is Dr. Ken House.
Okay, come on down. Back in the late 90s, NASA sent out a research announcement to invite bids and proposals from scientists who had ideas on ways to build a track that would utilize the forces of electricity and magnetism to provide an initial velocity, a little bit of a boost, give us some launch assist. One of the advantages of looking at the electric motor maglev concept is the fact that all of the energy required for the initial start from zero velocity up to the 400 mile an hour is provided on the ground. There's no friction, there's no wheels, and there's no heat and power loss that's associated with friction and rolling elements like bearings and wheels. With the opening of the recent maglev train, it's been demonstrated and proving that the technology is there. It's possible and it's feasible to move large, heavy objects at fairly high speeds using simply electricity and the force of magnetism.
The launch system is a fusion of two technologies, using the train and the plane to achieve a common goal. The train won't be going all the way to space. Instead, it will remain bound to its track as a flying vehicle is catapulted skywards.
This is the starting point, or the end of the motor, and in this section would be the levitation, and in the center section would be the linear motor. This bed here provides the levitation force, or the uplifting against gravity. These sets of coils here provide a stabilizing effect in the side-to-side direction.
Although NASA's models aren't yet ready to fly, they have proved that maglev trains could one day accelerate spaceships to over 1,500 kilometers an hour. Running through a tunnel of less dense gas like helium, friction from the air is reduced and the space train would have enough acceleration to launch its payload into orbit. But just how fast can the ultimate train go? The answer may be here at the Holloman Air Force Base in New Mexico. If any train deserves the prefix of ultimate, this has to be it. The Air Force's Hypersonic Upgrade Program, or HUP, has taken over 5 years and $20 million to perfect. This is potentially the fastest railed machine on the surface of our planet.
This is the Holloman high-speed test track. It's the most precisely aligned piece of rail in the world. Anywhere along it, it's 11 thousandths of an inch in terms of alignment, both laterally and vertically. This track is the longest in the world, the fastest in the world, the most highly instrumented in the world. The sled run that we're getting ready to do tomorrow will fire a narrow gauge sled down this that goes 9,600 feet per second, or about 6,500 miles per hour. It will set a new world land speed record for a railed vehicle. We're going 9 times the speed of sound, or Mach 9, tomorrow night.
At Holloman high-speed test track, speed records have regularly tumbled. The last record breaker back in 1982 smashed through Mach 8. 8 times the speed of sound, reaching over 9,800 kilometers an hour. Rail track is used for a variety of military high-speed research programs, from testing ejector seat systems to observing missile ballistics. These are ground-based tests that pave the way for flying prototypes. Most of these trains ran with little more than a mannequin at the helm, but it wasn't always the case. In the 1950s, human guinea pig Colonel John Stapp was regularly accelerated through 40 Gs, suffering broken bones and retinal hemorrhaging in one of the tests. The HUP train is designed to deliver a warhead into its target at the highest possible speed. This This train is too brutal for our railways, but the test will provide engineers with valuable hypersonic data. Mission HUP-80X G1 is hours away from launching into history. Dave Minto heads the team.
It'll be very exciting, but we'll also be very nervous because we're doing something that's never been done before. We'll be venturing into the unknown. New things can happen in physics when you go to where you haven't been. We've done an extensive amount of modeling and simulation to try to make sure that we know exactly what's going to happen. But modeling and simulation is only as good as the physics we know. So there is an element of the unknown.
Essentially a missile on rails, the HUP train is kept inside a protective tent until moments before the run.
All right, well, this is the first stage of our sled train. It's got 5 pupfish rocket motors, which is the first stage of the multiple launch rocket system. Burns for about 1.5 seconds. Then we'll light up a second stage. The second stage has 6 of the same rocket motor, the multiple launch rocket system first stage. The third stage rocket motor is a new rocket motor that we've had developed. We call it the Super Roadrunner rocket motor. It produces 228,000 pounds of thrust, burns for about 1.4 seconds. That'll get us up to about 4,000 feet a second. And then we'll light up a fourth stage, which is the same rocket motor again, 228,000 pounds of thrust. Now that'll get us up to 9,600 feet per second, or about 6,500 miles per hour.
This train is designed to cover its single 4.5-kilometre journey in a mere 6 seconds. Like a multi-stage space rocket, each section fires and then breaks away, accelerating the payload to a speed that's over 4 times faster than Concorde. But this train won't be stopping at a platform. It'll be slamming into its destination at full speed.
At the end, we'll deliver this payload, which is on top of the fourth stage here, into a target at a velocity that's, of course, 9,600 feet per second, which will have about as much energy as if a car ran into a brick wall at 2,000 miles an hour.
Instead of wheels, which would tear apart, the train uses reinforced steel slippers that literally slide along the track. Like NASA's maglev, to reach the highest possible speeds, the HUP will run through an atmosphere of helium. Russ Kurtz explains.
We've got this helium tube, we call it, which is basically 4 mil plastic that we create around the track, and we fill with helium. And helium, as you know, is 1/7 the density of air. It cuts down a great deal on the drag and enables us to reach these higher speeds.
As they learned in previous tests, moving through ordinary air at Mach 9 produces shockwaves so intense that steel can melt.
In this case, as this slipper was going down the track, what happened is you had shocks coming off the sides here, or shock waves, and impinging on this canard, and you can kind of see the melt. If you look really closely, that is a melted surface. It's more like a blowtorch came in here and started cutting this off.
From a safe vantage point 1 mile away, the world's media wait patiently for word that all systems are go and the fastest train on Earth can launch.
So you're going to hear 10, 9, 8, 3, 2, 1. It's going to resume, so there's a gap there. 10, 9, 8, 4, 3, 2, 1, 0, fire.
It's seconds before the sonic boom reaches the observers. Footage from the high-speed cameras shows the helium tube shattering as the train speeds through it. And still shots reveal hypersonic shockwaves trailing in its wake. The snapshots also show the payload lifting off before it hits the target. The impact itself is so secret that the footage hasn't been released. Clocked at 10,430 kilometers an hour, it's a new world record. At these speeds, this train would, in theory, take just 2 minutes to travel from New York to Washington, D.C. And just over 25 minutes to cross America. Like the jet, high-speed rail is now capable of supersonic speeds. Soon, it could surpass it as the ultimate way to travel.